Hi, Johan Pneumaticals is my name. We're back here for our tutorial series on the determination of internal forces by sight. This is gonna be the third one since last time I did the third one, but it just spent 15 minutes explaining what the internal forces actually are and the different tricks we use. So compression and tension for normal forces, basically within the beam from the right to the left for shear forces, and applying different jumps if you have single loads, or just applying a linear distribution if you have a distributed load. So for those explanations, please just go back to those previous videos. And for the bending moment, basically picturing how the beam is going to deform under the specific load, and then on the tensile side we're going to have the moment, the bending moment distribution we're looking for. If you have a single load, we're going to have like a sudden change in the of the slope of the moment, and if you have like a distributed load, it's going to be a quadratic distribution. So let's just start. For the explanation, please look those previous videos. So I'm going to start here. We should do level 1, level 2, and actually level 3. So let's go with it. Here we have a distributed load. So the shear force distribution is going to be linear. The distributed load is constant. Shear force distribution is going to be linear. On the left and the right support, we're going to have forces applied in the upward direction. So within the beam from the right to the left, we're going to have a jump on the right, then moving downwards linearly in the direction of the load, and then a jump upward at the left pin support. So this distribution in the middle is the right one. Shear force distribution again, so the reaction forces are going to be half of that single load in the middle. So on the left we're going to have half of that load going upward, on the right half of that load going upward too. So we read the beam from the right to the left, we're going to have a jump on the right, then it's going to be constant because we have no distributed load, then a jump downward because of the single load in the middle, then constant again because we have no distribution load and distributed load, and on the left side a jump back to 0 because of the vertical force at the pin support. So here we're interested with the normal forces. If you look at this beam, this column, a cantilever beam it is actually, we can see that this cantilever beam is neither stressed nor compressed. The distributed load we have there is only going to create shear forces and bending moments, but no tension in the beam. We could also picture this by doing the balance of forces in the horizontal direction, and we're going to see that the horizontal reaction force at the cantilever, at the clamp support, is going to be 0. So 0 for the normal forces. Okay, this is our best friend. I failed the last video, not failed, but I was explaining this. So we read the beam from the left to the right, and this is going to be a negative moment for when we read from the left to the right. So for the positive phase, it's going to be a negative moment, so we're going to do a jump in the opposite direction. So what is it going to be? It's going to be this one over here. And now about the force, it's basically this one. I want to say about the different component, which ones should be bigger, but yeah, let's talk about that another time. We're interested about normal forces here. Now look at this beam. It can be a little bit tricky, but that single load we have in the middle, that single inclined load, has an horizontal component. So what's going to happen is that the left part of the beam, so from the pin support to that single load, is going to be stretched. You can picture that pretty easily, right? But what's going to happen with the right side? The right side is neither compressed nor stretched because of the roller support. Because of the roller support, that part will just move along. Now, shear forces here, we look at the beam, at the cantilever beam in this case, from the right to the left. That inclined load has a vertical component and an horizontal one. We're only concerned about the vertical component here for shear forces. So what do we get? A jump downward. So at the end of the beam, a jump downward. This case is wrong. The middle one is wrong too, a jump downward. This one is right. Then it's constant because we have no distributed load. And then at the left side, so at the yeah, the support is basically a force going upward. The reaction force of the support, of the clamp support. Now, we're looking interested here in bending moments. We picture the beam. We imagine how this beam is going to deform. You can see that that last part, that part looking like a cantilever beam, the upper right part is going to bend downwards, kind of. The tensile side is going to be upward. So this picture here, completely on the right, this solution is wrong. This one could be right, but look, we have a distributed load. The moment can't be linear, okay? So the answer can only be this left one. Let's move forward. Yo, a distributed load on the inclined beam up there, yeah? But that distributed load is perpendicular to that beam, so it's not gonna create any normal forces in the in that inclined beam at all, okay? But you can see that the strut down there, that bar that's supporting the inclined beam, is gonna be compressed, and the whole distributed load is basically pressing that single column, okay? So negative force is compression, negative here, down there. Yeah, shear forces is what we're looking for here. We're just gonna read the beam from the right to the left, and at the right end we have a single load already going upward. So what do? A jump upward. So it could actually be this right answer. It's not gonna be though, because we still need to go back downwards because of the reaction force at the pin support. But this one, just about that information on the right side, could have been a right answer. The right one will probably, yeah, will be this one in the middle. So we're gonna have a jump upward, then constant because there's no distributed load, then jump back at the pin support, constant, and back up at the roller support that was completely on the left. Exactly the same system, but here we're interested in the bending moment. So now, basically just look at that cantilever looking part on the right side. What's gonna happen because of that single upward directed load? That cantilever beam is going to bend upward, meaning that the tensile side is going to be below in this case. So the moment is going to be on the lower part, kind of positive side for us here. So this right answer is wrong. This one is wrong. We don't have any single load to have a jump, any single moment to have a jump. So it will only be the left one. Distributed load here, so we need to have a quadratic bending moment. Of course, we're also gonna have a little jump, like a sudden change in the slope of the moment because of that single load between the two supports. So this one has a part that's completely linear. It can't be because of the distributed load. This one is exactly what we need with the sudden change. You can see that knick there in the middle. That's right. This one is completely linear. Is wrong. So here's the right answer in the middle. More about how the beam will deform, we could think about that another time because we have that time constraint here. Now, look at this one. On the first look, you could look at this and say, hey, so the load is perpendicular to the beam, so we don't have any normal forces, right? I said something similar a while ago, but look at the position of the support here. That's the main part. So if we do balance of momentum at the pin support, we're gonna find out that the roller support, they need to have a force acting downward, a vertical force acting downward, and that vertical force acting downward is going to put this beam under compression. So it's compression. It's not zero like in the middle, it's not tension like on the left, it's compression. Yeah, now we need to do level 3 actually. So here again, looking at the beam from the right to the left, we're gonna have like a jump upward, then downward because of that load, and then upward again. This left one is wrong. This one here is wrong. So it's the middle answer. That's right. Yeah. So what do we do here? Balance of momentum would be the best idea. Balance of momentum at the pin support, and then we can see that the roller support there has a reaction force of 0. And so the only thing that's happening here is that horizontal part of the system that's under compression. Compression means negative normal forces. Negative means not on the side of those interrupted line, but on the other side. So that was it. Bending moment, we have like the bending moment is what we're looking for here. We have a part with a distributed load, so the yeah, the curve needs to be quadratic. It also needs to have kind of like the form of, if you imagine that that horizontal part is like a rope, how would that rope deform because of the distributed load? So it will be exactly as we see here on the left side, on the in the middle case, but not on the right side. Now, which one is it? It's this one here. Why? Because passing through an angle, the value of the moment doesn't change. Okay, in the left case, it would have changed. It doesn't change. Except if you have like a single moment, but it wasn't the case there. So what's gonna happen here? This could actually be a truss. It could. It's not completely a truss, but it could actually be considered as a truss. So now the only part here that could have a shear force is like the white part, and now looking from the right to the left, we need to move downwards, so it could be this one. The horizontal part can have shear forces because it's a truss, right? So yeah, so what do we have here? The white part has a distributed load, it needs to be linear. So this one here on the right could be correct. This one here could also be correct. The shear forces in the vertical part should be 0. You can find that out by cutting through that vertical part and doing some of the force in the horizontal direction by considering the right side. You see we have a hollow support there. So no shear force in the vertical part. This one could be right, this one could be right. Now which one is the correct one? I see this. Yeah. Why is gone already? It's gonna be a little bit tricky just doing it right now. Look, that vertical part here looks like a bar, right? A simple bar that should normally not have any bending moment, but in this case we have a distributed load perpendicular to it. That's why we're gonna have a bending moment there. We're gonna have a bending moment, and the other side, what's gonna happen with the rest? Basically nothing. If you do some of the force in the vertical direction, there's none. In the horizontal direction, there's none. So only this one is correct, and that's it. We're done with level 3. We're gonna do level 4, 5, 6, 7, 8, whatever later. Okay. I've actually done all those levels, so there are like 8 levels in total. I've done all of them. You can find them in if you look for the series Schnittkraftmeister or ne Baustatik Schnittgrößen-Tutorial. I think that's how I call it. It's in German. So see you next time.